Thank, thank you. Hello, I'm Egor Namakonov, a master's student from St. Pete University. We work together with my researcher mentor Anton Podkopayev in the lab of instruments research. So this program is 3 streams. First stream, X address record 1, and then A variable, and then the record in Y, and stream 3, reading in Y, in Y, and then X. The question, can we have a result where we have 1 in all 3 streams? Let's look at the instructions. We start with first stream, then second, then third. And yes, probably such result is possible. Another question, can the same program be executed but have a result where C is 0? Let's execute the program in the same way, first, second, third stream. And here we know that X is 1, and that's why when reading X, again, we need to read here 1. Is it true? Not exactly. For instance, in C++ formula, it is okay to have C as 0. And why? In general cases, we do not have conditions for going to X address. In general case, these addresses can be non-atomic. C++ says that if the program has non-ordered request and non-atomic request, then it means that it means change of date, and C++ entails indefinite, undefined behavior. So to write multi-stream programs without any guarantees is impossible. That's why C++ offers the following. So make the instructions atomic. That's, in this case, we set specific regime of atomic access to them. Relaxed, one of the simplest regimes with no additional guarantees apart from excluding the data race. Will this behavior applicable after atomic instructions are on? Yes. And the reason is compiler can rearrange instructions in stream 2, and after this, 3 results where C is 0 can be possible. And thus, we approach the memory model. For a language, this is semantics of multi-stream nature that allows for many solutions of a program. For this program, C++ memory model says that when executing, you can have either results where everything is 1, or C is 0. So since we know that the second result cannot be achieved by executing the instruction, and we call it weak, but since C++ is offering us this, we also call it weak. So these optimization of compilers and the processors are possible. Since we want optimization, we want to allow related behavior. But sometimes we want to exclude such weak behavior to achieve more predictable behavior of programs. And in C++, you can do it through more strict modifiers of access. For instance, in our case, we had problem with X. That's why let's have 4 instructions that address it. Now let's have SC regime. This is the most strict regime of access, and in this program, it cancels all changes possible. Will it help us? If we launch this program on our notebook, we will not see such behavior. But if you have a server with power architecture, you can see such results. In this program, changes are prohibited. That's why such behavior is explained by deeper details of processes in power. And C++ solution offers the following: to increase regime of access for all parties, for SC, for instance. So we switch off optimization, and that results in lower efficiency. So it all starts with the following. The memory model of C++ actually gave the data race program undefined behavior. If we limit such behavior, we see the following. OCaml memory model is developed for OCaml multi-stream language, but these ideas can be applied in other languages as well. We see that in this model there are 2 regimes of access, non-atomic and atomic AT. AT looks like a C regime in C++. Let's try and execute it. Similar program in this model. We'll start 2 instructions, and at this point of time we will see data race for Y. variable because this is not atomic access, not balanced, but OCaml model offers us the local data race freedom. It says that the result of reading X doesn't depend on the race on Y. So when we execute the reading in Y, in Y, in X, we will only be able to read 1, and the result we know is already prohibited. So this is a useful feature, and it allows us to prove various specificities of behavior in the program despite the data race. To apply this memory model in practice, we need to prove that when we execute programs in real hardware, these guarantees are executed. But as we see, in power architecture, the similar program can be executed in a different way. But fortunately, we can see that processors execute not the initial program but the compiled one. That's why we need to require the same guarantees for a compiled program. And here we approach correctness of compilation term. So we say that it is correct, compiling scheme is correct if the behavior of compiled program is approved by OCaml model for the initial program. And in OCaml, we proved that it can be correctly corrected for x86 and ARM, but not for power, which is used in server equipment. And this was the goal, the task for our work. So memory models of languages and processors have discrepancies. They allow for different behaviors, and in order to reduce it, we use intermediary memory model. And thus, to achieve our goal, we just need to set the correct compilation scheme from OCaml into this intermediary memory model. And all the proofs are formalized in COG, and this proves its reliability. So this is interactive. COG is interactive, means instrument for theorem proving, that allows us to automatically check the proofs of various expressions in special language. But before we go to looking at correctness of compilation, we need a different layout. Execution. So we talked about execution, thinking about an order where instructions of the program are executed. But for such execution, you cannot find the order of execution that could give us the result in C, where C is 0. That's why we will not use this model. We need something that will allow us to show operations that are done on the memory and the links between the operations. And in such terms, it makes sense to think about graphs. OCaml, an intermediary model, offers us various executions through graphs. Every instruction of a program correlates with the peaks in the graph. So the left peak is W, right? And the parameters are X, 1, and the regime of axis, atomic. And the peaks of the same stream are linked with the program link. And then let's have a look at the upper tops of this entry value that was put by previous instructions. And this fact is shown as reads from. And the third peak reading is reading 0, which is in X before it became 1. So this reading is happening before the writing, and this is reads before. So we said that the models determine various executions through graphs. The model allows a behavior if the graph of execution is in line with the predicate. OCaml model doesn't want to cycles and graphs that contain reads from and reads before. We see that in this graph there is a cycle like this, and its behavior is prohibited by OCaml model. And now we can go to correct compilation schemes. So we remember that we want to prove that every execution of a compiled program in the intermediary model should be allowed by the OCaml model for initial model. But since we work with graphs, we can change it. We can ask for execution graphs from compiled programs that are available for intermediary model become a subsection of the graph of execution of the initial program that are available in OCaml model. So let's start with just trivial thing, something that substitute models. So compiled program will look like the initial one, but the regimes of access are different, and the graph of execution will look similar to what we saw before. And the model intermediary model also allows for such behavior because the no cycle requirement for such models. In the intermediary model, there is no such requirement. It allows for such behavior, and this scheme of compilation is incorrect because there is behavior that is allowed in the intermediary model for compiled program, but is not allowed for in a OCaml model for the initial program. How can we fix that? We see that reading in the second stream sees the entry in X, but we mean going through the graphs. Reading in stream 3 doesn't see the entry, and this behavior is shown in the cycle reads before. This reads before shows the reading of the obsolete entry. We want information on entries. We monitor the information to go through the graphs. After reading the value 1 in X, the second stream should give this information next down the stream and then somehow transfer it to stream 3, and it will, when reading in X address, should read 1. And we can guarantee such behavior through barriers of entry. These are instructions that prohibit some optimizations for compiler and the processor. There are heavy barriers that stop the majority of optimizations and more lightweight things that prohibit just part of them. And in order to select a barrier, we articulate the access regime for such barriers. For instance, we introduce barriers in regimes like release and acquire. And our program is compiled in the following way. We add barrier of one type for non-atomic entry first, second stream, and the third stream, another step. And the intermediary model guarantees that after stream 2 is executing the barrier and puts 1 in Y, and the third stream reads the entry and makes the instruction of the barrier, information on the X value will go to the stream 3. Let's look at the graph of execution. We see that here are the peaks correlating with the execution, and this behavior is blocked by intermediary model, despite it allows for cycles of this kind. But more specific case of such cycles, where all reads from either bring together peaks with SC points or they are fenced by barriers, and then this case in intermediary model is prohibited. So we exclude the not favorable behavior and come closer to correct behavior. But there are also other types of behavior that are different from OCaml, and we need to exclude them. That's why resulting compilation is challenging. And in our article, we proved the correctness for this, and as a result, we have the system of compilation, scheme of compilation for OCaml to IMM. We proved it to be correct and formalized it in calc. And it all gives us automated machine-verified compilation scheme for OCamlMM to power architecture, and that's what we wanted to achieve. This proof is available on the website of our project on GitHub. That's it from me. Thank you very much for your attention. Thank you. Questions? Sasha, any questions? Well, I have a simple question. Intermediary model, it abstracts the features of language or the processor. I hear about barriers in memory. Well, we can use C virtual machine with all the barriers in the memory and then put it on a separate processor. That's question 1. And question 2 I have as a person who doesn't know it well enough. Why OCaml, not ASCO? Answering your first question, what you offer is introducing intermediary execution. And here we use such model. Actually, this intermediary model is compiling not only OCaml memory model, but other models for C++.
So instead of just proving the correctness of compilation for every model and for every architecture, we're using an interim version, and we reduce the amount of job. Second question, OCaml. Why OCaml? I cannot actually tell you why it was offered, but right now we are working on removing parallels, and I know that some additional models are being constructed there, so it was used as one of the most better fitting. One more question? As far as I understand, there is no compiler right now for Bower that can support parallel code execution, and you are the pioneers in theoretically. You mean the OCaml model? Yes. Yes, that's correct. And the second question, didn't you think that you can actually do better? And the acquire release can work, but it's still something looking expensive. Yes, it seems like it is expensive. And we can use the memory barriers in every. And if you look into the compilation schemes that was offered by OCaml authors, it's not very much different. And it's going to not have one of the barriers, and the barrier in the second string is going to be weaker. But the OCaml model is quite strict, it's quite rigid, so the replacements of writings are not possible inside there, and they have very strong semantics in terms of records. So if we look into the scheme, you can see here that every specific element cannot be removed from here. The scheme will become incorrect, and the OCaml model has very strong guarantees, and the cheaper compilation is not possible. Thank you. Okay, clear. Is anyone listening to interpreting? Please raise your hands if you're listening. You're listening? Yes, but there is no backup support. x86 can be optimized in laboratory. Okay, what we do want so it's going to be working the same because there's different architecture, I'm not sure. Okay, yeah, understood. Let's have the mic. So as for quality, we actually proved it in our article. As for productivity, this was not something that we touched in our job. So, but it shows that you can get something. Okay, good. Thank you. You're all. Thank you.